I want you to imagine, just for a second, that you just hired the most brilliant assistant in the world.
Okay.
I mean, this person is an absolute genius. They can write complex code. They can analyze massive data sets. They can basically, any obscure problem you throw at them.
Right. The dream hire.
Exactly.
Yeah.
But there is one massive glaring catch.
Yeah.
Every single night when they go to sleep, their memory is completely wiped.
Oh, wow.
Yeah. So the next day, when you ask them to do that exact same task, they just look at you blankly. They have to figure out the entire protocol from scratch all over again.
Which creates this really bizarre bottleneck for productivity. I mean, you have access to raw, unadulterated intelligence, but absolutely zero compounding knowledge.
Right.
The assistant never actually gets faster at their job.
And the crazy thing is that frustrating reality, that is exactly how most large language model or LLM agents operate today.
Yeah, they really do.
They are brilliant, but they are fundamentally forgetful. They treat every single prompt like it's the first time they've ever seen the problem. But what if we could fix that?
That's the big question.
Welcome to the Deep Dive. Our mission today is to unpack a state-of-the-art research paper that just might change how we interact with AI forever. It's titled MUSE-Autoskill: Self-Evolving Agents via Skill Creation, Memory Management, and Evaluation.
Yeah, so this is a May 2026 paper authored by researchers from ByteDance and the Rochester Institute of Technology. And they are addressing a ceiling we've hit in AI development.
Right.
Because as the tasks we assign to agents get more complex, say, writing enterprise-level software or running scientific simulations or managing cloud infrastructure, raw LLM reasoning just isn't enough anymore.
You can't just throw a massive 1,000-word prompt at a model and hope it navigates the nuance.
Exactly. Agents need what the researchers call skills, which are basically these reusable modular units of capability.
Okay, let's unpack this, because people have tried to give AI skills before, right? We've seen projects where agents try to save their workflows.
We have, yeah. There is a whole lineage of systems that attempted to synthesize skills automatically. You look at early systems like Voyager.
Oh, right, the Minecraft lab.
Yeah, exactly. A Voyager built executable code library so an AI could play Minecraft. And then you had general purpose systems like Autoskill or EvoSkill. But the fundamental flaw in those older systems is that they treated skills as isolated, disposable artifacts.
Disposable.
Right. They would generate a string of code, use it once, and then effectively abandon it. There was no structured per-skill memory that accumulated experience over time.
Ah, I see.
And furthermore, they didn't have robust unit test validation.
So if I can use an analogy here, it's like you have a world-class chef, which is our LLM, who invents this mind-blowing Michelin star recipe on the fly during a dinner rush.
Okay, I like this.
But instead of putting it in a master cookbook, they scribble the steps down on a paper napkin. And at the end of the shift, the napkin just gets thrown in the trash.
Yep.
The next time a customer orders the exact same dish, the chef has to stand there, stare at the ingredients, and reinvent it all over again from first principles.
That captures the inefficiency perfectly, because every time the chef has to reinvent that recipe, they introduce the risk of a new hallucination.
Right.
Maybe today they forget a step, or they take twice as long to prep the ingredients, or they just burn through valuable computational resources figuring out a procedure they already perfected yesterday.
Right, which gets expensive.
Yeah.
So if throwing away the napkin is the root of the bottleneck, the obvious question is, how do we build a permanent self-updating cookbook?
Exactly.
And the solution proposed by the ByteDance and RIT team is the MUSE-Autoskill framework.
Yes. So MUSE stands for Memory Utilizing Skill Evolution. And the core argument of the paper is that a skill shouldn't just be a one-off text output. It needs to be treated like software and managed through a unified lifecycle. They break this lifecycle down into 5 distinct stages: creation, memory, management, evaluation, and refinement.
I will look closely at the anatomy of one of these skills, because when I was reading the paper, I realized it's not just a simple text prompt. It's an entire structured directory.
Yeah, it actually mirrors Anthropic's agent skills format, which serves as an open standard. When the MUSE agent creates a skill, it generates a comprehensive package.
Like a whole folder of files.
Exactly. At the center is a file called skill.md. This markdown file defines the interface. It explicitly states what the skill does, the exact parameters it needs as inputs, and the schema of what it outputs.
Okay, so the instruction manual.
Right. And beyond that core file, the agent generates subdirectories. It creates a scripts folder filled with executable Python or shell code. It can create a resources folder for auxiliary data. And crucially, it builds a tests folder.
Wait, let me stop you there. It builds a test folder.
It does.
So the AI writes its own test, takes the test, and then grades itself. Isn't that a massive conflict of interest? Like a college student writing their own final exam and handing themselves an A.
You would assume the AI might just, rubber stamp its own work. But the grading mechanism here isn't subjective at all.
Oh, really?
Yeah, this is where the evaluation and refinement stages completely change the paradigm. When the agent uses its built-in skill create tool, the resulting skill isn't immediately trusted.
Right.
Before it is ever allowed to be saved to the permanent skill bank, it has to pass those unit tests it generated. And these tests are executed in a strictly isolated, objective sandbox environment.
So it's executing actual code in a terminal. It either compiles and runs successfully or it crashes. There's no room for the AI to hallucinate a passing grade.
Exactly. The system utilizes an automated evaluator that runs the test scripts independently. If the code throws a syntax error or if the output format doesn't match the schema defined in that skill.md file, the skill fails the evaluation.
It just fails.
Right. But it doesn't just discard the attempt and give up. If it fails, an automated refiner takes over.
Oh, wow.
It ingests the error trace from the terminal, figures out exactly which line of code broke, patches the code in the scripts directory, and initiates the test again.
So it fixes its own bugs.
Exactly. It creates a closed loop of create, evaluate, refine. And only when the test runs flawlessly is the skill registered to the agent's permanent cookbook.
So to extend that chef analogy, it's not just writing the recipe down and putting it in a book. It's the chef writing the recipe, forcing a sous chef to cook it exactly as written in a locked kitchen, which is our sandbox,
Right.
then tasting it, fixing the salt levels, that's the refiner. And only when the dish is perfect do they laminate the page and put it in the permanent binder.
That is a highly rigorous lamination process,
Right.
and it guarantees that the agent's permanent library only contains robust, functionally verified tools.
That structural rigor makes a lot of sense. But writing, testing, and refining all these complex skills with multiple scripts and metadata files, that requires reading massive amounts of generated text.
It does, yeah.
Doesn't that overload the agent? Because if you're listening to this and you've ever used ChatGPT for a long project, you've probably noticed that it suddenly forgets a rule you gave it 20 minutes ago.
Oh, absolutely.
The context window just hits a wall and the system breaks down.
Yeah, the researchers actually refer to that exact phenomenon as token doom.
Token doom.
That sounds ominous.
It is, especially for agents. The model they use for their tests, GPT 5.5, has a hard limit of about 200,000 tokens. They set their safety threshold at 180,000 tokens just to leave some breathing room.
Okay.
So to keep the agent from hitting that wall while managing all these complex skills, MUSE introduces two major innovations. First is skill-level memory. Every single skill directory gets a hidden file attached to it called memory.md.
Like an evolving diary dedicated to that specific tool. Yes, exactly like a diary. As the agent uses a skill across different tasks, maybe weeks apart, it writes down operational quirks, caveats, and lessons learned into that append-only log.
Oh, that's clever.
For instance, the agent might log, warning, the PDF extraction script times out if the target file is over 100 megabytes. Chunk the file first.
Right.
The next time the agent loads that skill for a new task, it reads the .memory.md file first. It instantly knows to handle large PDFs differently, bypassing the need to fail and relearn that limitation.
It's accumulating wisdom, not just raw code.
Exactly.
But even with a smart diary, the immediate working memory of the AI, like the context window of the current session, can still get overloaded with thousands of lines of terminal output during a complex task.
Right, which brings us to their second innovation. To solve the active session bloat, they engineered adaptive context compression, which operates on a DAG react loop.
Okay, DAG react loop. That sounds incredibly dense.
It sounds worse than it is. We can demystify it quickly. A directed acyclic graph, or DAG, just means a flowchart that only moves forward. There are no infinite loops allowed.
Okay, a one-way flowchart. Got it.
Right. And React is simply the loop of reasoning and acting. So visualize the agent's workflow as a flowchart. It makes an observation, reasons about it, takes an action, gets a result, and draws a new node on the chart. All right. As that flowchart gets massive, getting dangerously close to the 180,000 token limit, compression kicks in automatically.
It essentially edits its own working memory to save space.
It does so in 2 tiers. Level 1 compression scans the flowchart for individual oversized nodes.
Okay.
Let's say the agent ran a database query and got back a massive block of raw text that is over 15,000 tokens. The system takes that single bloated node and replaces it with a compact, high-level summary of the data.
Shrinking the bulky paragraphs. But what if there are just too many small turns? What if the sheer number of steps is the problem?
If the total context is still threatening the threshold after level 1, it triggers level 2 compression. And this is a lot more aggressive.
How so?
Level 2 collapses a whole historical chain of past turns, say 10 steps of trial and error, into one single summary node.
Wow.
However, there is a critical safeguard. The system is hard-coded to always pin the first 5 turns and the last 5 turns. Those are never subjected to compression.
I think I see the architecture here. It's like reading a massive 1,000-page fantasy novel.
Okay.
You don't need to remember the verbatim, word-for-word dialogue from a tavern scene in Chapter 2 to understand the stakes of the big battle in Chapter 40.
Right.
You just need the cliff notes for the middle stuff.
Right.
But you absolutely 100% need to remember what is happening right now in the chapter you're reading.
Yeah.
That's the last 5 turns. And you need to remember the original premise of the quest. That's the first 5 turns.
That is a perfect analogy. By locking down the original instructions and the immediate working state, the agent never loses the plot of why it's executing a task.
Yeah.
But by compressing the messy middle, it frees up enough token space to keep working indefinitely without crashing.
So context compression keeps the system from crashing, and the skill diary keeps it from repeating mistakes. It's a beautiful theory.
It is.
But just because an AI doesn't crash doesn't mean it's actually doing good work. Did they test if a self-correcting agent actually outperforms a human writing a really good prompt?
They did. The paper includes a rigorous benchmark called Skills Bench to prove exactly that.
Okay.
They tested MUSE against 51 highly complex, real-world tasks across 4 domains: science and engineering, data analysis, document processing, and operations and planning. And to prevent any data contamination, they ran these evaluations inside isolated Docker containers.
Which means no environmental leaks, just raw performance in a sterile environment.
Exactly. When they ran the MUSE agent completely bare, meaning no skills, just its raw GPT-5.5 reasoning trying to figure out the task from scratch, it scored 53.19% accuracy.
Okay, basically a coin flip.
Right. Then they injected human-authored skills into the system. These were skills meticulously hand-coded by human developers. The accuracy jumped to 68.40%.
A solid 15-point jump.
Mm-hmm.
So it proves that giving an agent structured tools works better than raw reasoning.
It does, and it also beat rival state-of-the-art agents like Codex and Hermes on that same benchmark. But the researchers pushed it further.
Sure.
They took the successful trajectories where the bare MUSE agent managed to solve a problem and had it use the skill create tool to package up its own methodology into a new skill.
Okay, here's where it gets really interesting. What happens when the agent relies on his own generated cookbook?
When MUSE ran the benchmark again using its own generated skills, on the 35 tasks where it successfully built one, it completely crushed the human baseline. It scored 87.94%.
It beat the human experts by almost 20 percentage points.
It did.
But humans wrote the initial baseline skills.
Yeah.
Why is the AI so much better at writing instructions for itself?
The mechanism driving that success is procedural explicitness. Humans intuitively leave a lot of assumptions unsaid when we write instructions because we expect the reader to share our common sense.
Right, we take shortcuts.
Exactly. The AI doesn't rely on intuition. When MUSE generates a skill, it spills out exact data schemas, specific failure modes, and highly rigid step-by-step procedures.
I was looking at the specific examples of this in the paper, and they eliminate exactly how that works. There was a task called adaptive cruise control.
Yes, the physics simulation.
Right. The AI had to build a discrete PID controller for a car simulation. Without a skill, it thumbered the math and only figured it out 40% of the time.
Mm-hmm.
But when the agent generated its own skill package for this task, it didn't just write a prompt saying build a controller, it wrote the actual discrete PID equation into a Python script. It added gain tuning heuristics, and it even programmed anti-windup protocol so the car's simulated motor wouldn't accelerate out of control when hitting a threshold. When it used that self-generated mathematically explicit skill, its accuracy shot to 100%. Flawless execution.
It's incredible. And a similar breakthrough happened with the Flink query task, which involved writing complex Apache Flink Java jobs for microsecond event time sessionization.
Which is incredibly dense back-end engineering. The Bear agent only had a 20% success rate on them.
Yeah, the Bear agent fails at 20% because Flink requires highly rigid boilerplate Java syntax.
Very unforgiving.
Right. General LMs have a tendency to drift away from strict syntax over long outputs. They try to get creative where creativity literally breaks the compiler.
Right.
But when MUS generated this skill, it didn't just tell itself to write Java better. It wrote a reusable Python script that templated the exact Java boilerplate needed for Flink.
Oh, that's smart.
It effectively removed its own vulnerability to syntax drift. Using that script, its success rate jumped to 100%.
It builds guardrails against its own weaknesses.
Yeah.
But I have to ask about the computational cost here.
Okay.
Generating all these files, running the unit tests in the sandbox, refining the code, doesn't that cost an absolute fortune in cloud compute?
The researchers address the economics of this directly, actually. The generated skills are what we call Pareto optimal. There is absolutely a heavy upfront cost. It takes roughly 383,000 tokens of compute to synthesize, sandbox test, and refine a skill the first time.
Which is a massive API bill for one task.
It is. But once that cost is paid, the skill is permanent. And deploying that permanent skill is substantially cheaper than forcing the agent to reason from scratch every single time.
Wait, how is forcing the AI to read an extra skill directory cheaper than just asking it a question?
Because it stops the AI from wandering down expensive dead ends. Without a skill, the agent might try 5 different incorrect approaches, generating tens of thousands of wasted tokens on failed code before it figures it out.
Ah, I see.
With the skill guiding it, the agent gets straight to the point. The data shows that using a self-generated skill drops the median latency to solve a task by 273 seconds.
Oh.
And crucially, it cuts token usage by 85,000 tokens per task compared to running Bear. So yes, you pay 383,000 tokens up front, but you save 85,000 tokens every single time you use the skill thereafter.
It pays for itself in less than 5 uses.
Exactly. It's better, faster, and over the long run, drastically cheaper.
It's an infrastructure investment. Pay the construction cost up front, reap the operational dividends forever.
That's the idea.
Now, there's one more experiment in this paper, and it really pushes the boundaries of what we consider AI capability. Building a highly optimized tool for yourself is one thing, but I'd assume that taking a ByteDance-created skill framework and dropping it into an entirely different AI architecture would cause massive compatibility crashes.
You would think so, yeah, given how siloed AI models usually are. Historically, if you trained a reinforcement learning agent to excel at a task, that knowledge was mathematically baked into the specific neural network weights of that specific model.
Right.
You couldn't just extract the knowledge and hand it to a competitor's model.
It was locked in a black box. But the ByteDance team took the text files and Python scripts that the MUSE agent generated, the skill.md, the scripts, the .memory.md, and they just dropped them into an entirely different agent called Hermes.
Yeah, because MUSE externalizes its learned knowledge into standard universal formats like Markdown and Python, the knowledge is entirely portable. Hermes, despite being a different architecture, could read the directories perfectly.
And how did Hermes perform using tools it didn't build?
Hermes's baseline accuracy on the benchmarks was 47.89%. When it loaded the skills generated by MUS, its accuracy skyrocketed to 58.40%.
No.
It closed 79% of the performance gap between its bare self and its performance when using skills hand-coded by human experts.
That's huge.
And furthermore, just like MUE, Hermes saw a massive efficiency gain. Its processing latency dropped by 30%. The knowledge transferred flawlessly across different artificial minds.
That is actually a bit unsettling. The data shows that the MUSE skills are 2.2 times longer and more detailed than the human-authored ones.
Right.
It means we are entering an era where AI is creating standard operating procedures that are almost too dense, rigid, and procedural for humans to bother reading. But they are perfectly optimized for machine-to-machine learning. Another AI can just ingest the folder and instantly become a domain expert.
If we connect this to the bigger picture, it fundamentally moves us away from AI capabilities being these opaque matrices of weights. It turns AI problem-solving into human-readable, auditable, and endlessly transferable software assets.
So what does this all mean? If we zoom out for you, the listener, and think about the software ecosystems you rely on every day,
Yeah.
we are rapidly moving away from an era where human engineers have to painstakingly hand-wire every single data pipeline or API integration for an AI agent.
Absolutely.
Instead, we are entering an era of shared, continuously evaluated skill ecosystems. If an autonomous agent in Tokyo figures out a novel, highly efficient way to parse a messy, corrupted Excel file, it can package that method into a tested skill and share it.
Yeah.
Instantly, every other compatible system on the planet gets an upgrade without a human writing a single line of code.
It is a profound shift in how software infrastructure will scale. However, we do need to ground this in the current reality. The system is incredibly powerful, but it is not magic. In the skills bench evaluation, for 16 out of the 51 tasks, the MUS agent couldn't generate a skill at all.
Because of the phase 1 bottleneck.
Exactly.
If the bare agent can't solve the task even once through raw trial and error, it has nothing to learn from. It can't build a skill for a problem it fundamentally fails to understand.
Right. Those 16 failed tasks were highly specialized, dealing with obscure production telemetry tools or complex numerical partial differential equations. Things that a general language model just doesn't possess the baseline intuition to stumble through. The frontier of this research will be figuring out how agents can learn skills from partial successes, or how they can analyze their own failures to bridge those gaps.
But even with that bottleneck, the 87% success rate when it does understand the task is staggering, which leaves you, the listener, with a final thought to mull over. If we are entering a world where AI agents can identify a bottleneck, write their own universal software package to solve it, write the unit tests, verify the code in a sandbox, and refine it until it's flawless, how long until human developers stop writing standard code entirely?
It challenges the very definition of a software engineer.
What if in 5 years, software engineering isn't about writing functions or debugging syntax? What if human developers simply act as librarians, curating, governing, and observing a massive, self-evolving library of AI-generated skills?
It changes what it means to program a computer.
Think back to that brilliant, forgetful assistant from the beginning of our conversation. We finally figured out how to give him a permanent notebook. And it turns out, they write operating procedures a lot better than we do. Thank you for joining us on this deep dive.